Okay, so good morning everyone. Welcome to lecture 19. So this is, by the way, from chapter 4 of the book. Okay? And what we are doing is mechanical balance laws. So remember in the last class we said what's the motivation? We are trying to derive equations which can be used to solve the unknown deformation. Okay, so as far as the motivation is concerned, we want to derive equations which can be used to solve for the unknown deformation map. Okay, which is this y hat, the function y hat, that's a function of x, no? So this is an unknown and it's also a function of time. So derive equations to obtain this unknown. And you will see that as we derive the equation, you will actually start having more and more unknowns. But this is the basic unknown that we want to derive, that we want to actually obtain. And the first one we had already derived was the mass continuity equation. Right? And we saw two forms of it, isn't it? The one was the Eulerian form and the other one was the Lagrangian form. In the Eulerian form, it was a differential equation and it had the following form. I guess it was rho dot plus rho times divergence of velocity, that's equal to 0, or you write in the following form del rho del t plus divergence of rho v, that's equal to 0. Right? I hope I have written this correctly. If you guys feel that I am not correct, then please let me know. So this was the mass continuity equation and this was the Eulerian form, meaning that this rho is an Eulerian density per unit volume, current volume. And we also had the Lagrangian form, so this is Eulerian form. And then you had the Lagrangian form, in which we had the following, that rho, we said rho hat, that's a function of x. Yeah, so these are bars, of course. Okay, and that's equal to rho bar into j. So that's like an algebraic equation. It's not a differential equation. I mean, it's not a differential equation in time. It's of course a differential equation in space, because j is gradient of the deformation gradient. Sorry, j is the determinant of deformation gradient. So it's I can say it is algebraic in time, because there is no time differentiation present here. Okay, and remember that somebody had asked a very nice question, and I said that this rho hat of x is not equal to rho bar y of x comma t comma t. They are two different quantities. Okay, and for this reason, I thought that maybe I'll make this rho naught, because till now whenever I use hat and bar we were equating it. So not to have any confusion, I will just make it rho naught. Okay, because they are two different quantities. They are not denoting the same physical quantity. One is, of course, both are density, but one is mass per unit deformed volume and the other one is mass per unit undeformed volume. Okay. So that's the mass continuity equation. Then of course, then we have to think of what more equations can be used and we can apply to this continuum body, and we can come up with some equations. So of course, when you did rigid body mechanics in your undergraduate class, what equation did you use to obtain the equations of rigid body? Can you guys recall? So of course, you have used Newton's second law, remember? For a particle, it is force equal to mass times acceleration, isn't it? That's in the in inertial frame, you can write that. With respect to inertial frame, net force on the particle is equal to mass times acceleration. And often people also call it linear momentum balance. And that's because the mass times acceleration can be also thought of as ddt of linear momentum. Right? So that is the principle that we will use now. Linear momentum balance. Okay, so we'll call it linear momentum balance. And in short, it is LMB. Okay. And let us see how does it look like for a continuum body. When the body is deforming, how does it look like? So remember that here is your body in the reference configuration, which has deformed. So this is reference, this is current, and of course the region occupied is, this is R ref, right? Whereas here it is R, and you can say maybe RT, right? So let me put RT, T as a superscript. And then a part of this body. So of course, this is the region occupied by the body, whereas the body itself is the collection of particles, right? And you remember that we applied the mass continuity to a part of the body. Okay, so if I also write the part here, so this is the body collection of particles, and think of a part of the body. Okay, and let us call it big P. Okay, this is a part of the body, big P. Any particle is just a small p, right? And this part of the body is big P. So we know that this gets mapped here, no, to that map, configuration map. This is chi ref, and you pass to it particle and time. But here, of course, it is just a particle because it's the reference. Whereas over here, it's this configuration chi as a function of p comma d. And this red part of the body, whenever we say part of the body, we are basically identifying fixed set of particles of the body. Okay, we are identifying fixed set of particles, and we will be applying all the balance laws to fixed set of particles. Okay, it is very important. You see, the Newton's second law, it is applied to a fixed set of particles. You can't apply it to a system whose particles are changing. You cannot apply that. Remember that. So all the balance laws, we always apply it to a fixed set of particles. I'll also write that here. all the, or I should say all the physical principles are applied to fixed, or you can also say identifiable set of particles. So basically, the system that you have taken, its particles must not change. It should not happen that one particle is going out of the system and another is coming in. That should not happen. Your system should be closed with respect to particles. Of course, it can exchange energy and heat, but it must be closed as far as mass transport is concerned. Okay. So somebody is asking, sir, we can apply LMB to flow systems. Of course, you can apply LMB to. So what we are doing is applicable to fluid, solid, everyone. Okay. So now looking at this part of the body P, this will occupy some region here, which we can call D, right? And that over here would become dt, isn't it? So it's a part of the, it's a region for the part of the body, d and dt. So, we now want to apply this linear momentum balance principle to this part of the body dt. See, it should be applicable to any part of the body. And therefore, we have chosen this dt. If you, of course, take the full body, then it is RT. So let us, and because you can apply it to any part of the body, let us choose this dt, okay? So I'm going to choose this dt here. So this is your dt. I think in the book it is subscripted d, so I'll write it as dt. Scripted d, sorry. So let's make it also appear like what it was a verb. Okay, so when you want to apply this LMB, linear momentum balance, then the physical principle says that net external force, isn't it? This is what the physical principle, net external force on a system which has to be closed, okay? This is equal to d by dt of the linear momentum of the system. And let us say the linear momentum we denote by the vector p. Okay? The part of the body is scripted p. The part of the body is scripted. See, this is the part of the body scripted p. But here it is straight p and the vector p. So that's the linear momentum. And of course, it is done in inertial frame. You can, only in inertial frame it looks like this. If it is not an inertial frame, you have some extra term. And you see, if you think that you want to apply this to a system whose mass is also changing, then it is not in this form. You will have again some extra term. Okay? So that's what I meant when I said that LMB can be applied only to, so LMB in this original form can be applied only to a system which is closed with respect to mass transport. Okay, so now our job is then, if we want to apply this principle, we have to do two things. One, to know how to write down the total linear momentum of this part of the body, dt. Okay, and the other is to sum all the external loads that are acting on this body. Remember that this is just a part of the body, and here is your whole body, right? So it has other part also. So the body has been divided into two parts. One is dt and the other one is rt minus dt, right? So this part is rt minus dt. So can someone tell me what are all the external loads or external forces which is acting on this dt? So to do that, we have to draw the free body diagram, for which you have to isolate this dt. So this is what we have done here. Okay, this dt has been isolated. So now we have to show all the external loads which act on this dt. So can someone tell me what are all the external loads that are acting on this dt? Think of this being a physical body, any scenario, and what are all the forces that are acting here? Subham says body force, surface force. Can you be more specific? What is body force? What is surface force? Gravitational force. Yes, this is more a specific example of a force. Any other kind of force that can act on this body? Can you guys just think of any general state or any general system, all kind of possibilities that you can think of, and let me know what are the various forces that can act on this body. Gravity, friction. Why should friction be there? Electromagnetic, yes. If the body is magnetically activated, then and you put it in a magnetic field, it's going to see some force. Pressure force. Why should pressure force be acting on this part of the body? You see this, it's a part of the body which is inside the body. How is pressure force going to act on it? Centrifugal force. Centrifugal force is not a force. Okay, it is not a force, remember. It's a pseudo force, no? It's not a physical force. Elastic force. What do you mean by elastic force? Attraction and repulsion. Let's be more clear. What do you mean by buoyancy? Viscous force, pressure force. Again, why do you say pressure force? Because it's a part of the body inside the body. So fluid cannot exert force on it directly, right? Fluid will exert force only on the surface of the entire body, not on this part of the body that is inside the body. Stress. So Karthik is saying stress. So that is, of course, a very important force that is acting here. Reaction force. Which reaction force? Support reaction. But where is the support? Support is not directly applied to it, no? Support may be acting on the full body, to a part, to a surface of the full body, but this dt, in the red, it's inside the body. So support is not uh, directly connected to this body, no, to this part of the body. Subham is saying differential pressure force in terms of buoyant force. Again, that is again not true. See, you have to identify, you first think who is applying that force and then think of What are all the forces? Somebody has to apply. And the moment you think of that, most of the confusions will go away. For example, when you said support force, so it's being applied by the support, but support is not applying to dt directly, it is applying to the surface of the full body. It is acting on the full body, not on this dt. Therefore, when you draw the free body diagram of dt, support force will not be there. Similarly, when you say buoyant force, so it is acting, it is actually the resultant of the pressure forces, that from the fluid. And those pressure forces are acting again on the surface of the full body, not directly to this dt. So when you draw the free body diagram of dt, that will not be present. But of course, gravitational load, it is acting on this dt, because gravitational force is from particle to particle, no? So to each particle of this body, there is some gravitational load. Okay, so I think we have had a lot of messages from you. Let's now concretize what are the various forces which are acting. So I will again draw this part of the body. So one, of course, we all saw that the other part of the body may be applying some force on this part of the body, right? And that would actually be present all along the surface of dt, isn't it? Let's use different color. It's like a reaction from the other part of the body. So this is, and it's also called internal reaction because the surface is internal to the body, So it is internal to the entire body, but it is external to this part of the body. Okay, so I should write just here reaction from the other part of the body. Okay. And this, of course, it is internal reaction for the entire body. But it is an external reaction for this part of the body. And you see that it's it can only act when there is a direct contact, and therefore it is acting on the surface of this dt. So it is acting throughout the surface of dt. Do you know what is this reaction called? Anyone? Traction. That is true. It is called traction. It has a unit of force per unit area, and it is called traction. And we will denote it by T. Okay. So this is called traction. This internal reaction, as far as the entire body is concerned, it's like an internal reaction. When you cut an internal surface, one part of the body is applying something on the other part. So that force is traction, okay? And it has a unit of force per unit area. It's a very important force, and we'll call it by T. So it has unit of pressure and it is not perpendicular to surface. It does not act perpendicular to surface. It can be at a tilted angle also. So if it is at some angle, then the perpendicular part is called normal component of traction, whereas the tangential part is called shear component of traction. Right? You all have seen this in undergraduate class. So it has two components. Normal and shear component. And you see, this is not just for solid body, it is for a continuum. It can be also a fluid. You can likewise think of a part of the fluid body. And again, same thing. Whatever I'm saying holds for both solids and fluid. Something more about this traction. So as we saw that it has the unit of pressure and it has two components, normal and shear component. And it will vary from point to point. So traction is therefore a function of the point where it is acting. What else is this a function of? N. So that's a normal N, surface normal. So yes, you guys are right. It's also a function of the outward normal to the surface of the body, which is under consideration. Outward normal to the surface of the body under consideration. And of course, it can also be a function of time. Yes, very good. So maybe I'll put that T first, and then I'll say it's also a function of N, no? So with this. And do you guys know how are these two related? T of y comma t n and t at the same point y and time t but of minus n. Do you guys know how they are related? So let us see what's the meaning of this. So again, think of the entire body. And cut a section. So think of this section here. And suppose the normal to this section, this is n. Okay, so for the left part of this body, for the left part, which is like this, and this is the cut surface. Here's the normal n. Okay, whereas for the right part, let me draw in blue. So the normal for the right part, the outward normal, that's minus n, isn't it? So the traction that will be acting on this surface, that as per this thing here, we'll say T, and then it could be any point y here, let us say y, comma T, and then outward normal n. Whereas for the corresponding point over here, we should write it as y, comma T, and then outward normal minus n, isn't it? What they are action reaction pairs. They have to be action reaction pairs. So the left one is the force applied by the right part of the body on the left. This one is the force applied by left part of the body on the right part. So obviously they are action reaction pairs, and therefore they are negative of each other from Newton's third law. Okay, so therefore this is equal to negative of this. And there is actually something more. How this traction depends on normal n. So all of you must have done it in your undergraduate class, that you guys remember the tetrahedron argument. There's some tetrahedron argument. According to which you can say that this traction T is equal to a stress tensor, so now you have a stress tensor sigma, which is just a function of y and t, not a function of normal, times the normal n. So the dependence of traction on normal is linear. It's linear in n. So it is sigma times n, where the sigma is called Cauchy stress tensor. Okay. Has anybody not seen this? But you must have seen this. See, it is taught, it's a part of the undergraduate course. Okay, so this is all about traction, and you'll find something more in the book. When you read chapter 4 of the book, it has several nice things written there. Please definitely go through it. I can't cover all of them here. So this was just one of the forces acting on this dt. What other forces are acting on this dt? And you see that this force is kind of surface force because it is acting on the surface of this dt. And surface force, therefore, it also has a unit of force per unit area. So that when you integrate over the surface of the body, you get the total force. Okay. So it also, I'll just write here, it's also kind of surface force, which some of you have also pointed out. It acts only through contact. So somewhere, some places you will also see it's called contact force. It comes under the category of contact force. Okay, under the category of contact force. But this is not all the forces that is acting on this dt. There's something more, right? And some of you already said, for example, gravitational force or electromagnetic force. So those forces that are acting on this dt, it does not require direct contact. For example, who is applying gravitational force on this part of the body? Is it the other part of the body which is applying? Who is applying? Can someone tell me? It's being applied by the Earth, right? And Earth is nowhere in contact with this part of the body. And also it is acting on every particle of the body. It is acting everywhere, all throughout the body. Again, kind of non-contact force because you don't need contact. Gravitational force is one such example. Then of course there are many more forces like electromagnetic force, electric force, magnetic force. So you have a magnet, two magnets, they just, you know, they can repel each other or attract each other without being in contact, right? They are far apart, still they are exerting force on each other. So it's a non-contact force. So such forces, as far as this contingent body is concerned, they can all be categorized as what is called body force. Okay. And we'll denote it by B for body force. And it's a function of, it can be a function of the position y as well as time t. And this is force per unit volume. Okay. So these are all per unit current volume, by the way. Okay. It's current volume. Similarly, here distraction is also force per unit area. It's the force per unit current area. Okay. So I hope things are clear about the nature of force. How can this body force be a function of y? Can someone tell me why should this be a function of y? Or can you think of an example where this body force is actually a function of y, the location of the particle? So the potential mgh, but g we treat as a constant, no? Non-uniform field which is causing this body force. Okay, yeah, that's a, yeah. So Vipul says at celestial scale, yes, at celestial scale, gravitational force can become function of y. Just think of moon and earth contacting each other. Then the distance, what is the gravitational force? It is gmm by r square, right? Gmm by r square. So it is proportional to the, it is inversely proportional to square of the distance. So moon and earth, so earth is somewhere and moon has different particles. So different particles of the moon are at different distance from the center of earth. Therefore, different particles of the moon experience different body force. Okay? And therefore, this body force can be a function of y. Similarly, electrostatic force, of course, it is very much like the gravitational force. So they will also induce a body force which will be a function of y. Okay, so that's why it is a function of y. And why is it a function of time? Can someone tell me why is it a function of time? Why think of an example where it is a function of time? Can you do it for gravity? Can you do it for the gravitational force, that it being a function of time? Both y and t? Anyone? So Manoj says yes, its distance is changing with time. But no, because the changing distance, it is all captured through y. See, y is also a function of time, right? So that is already captured in y. There can't be any explicit dependence on time. But of course, if you have an electromagnetic field which is changing with time, then the force due to that field will also be a function of time. So for such forces, you can have time dependence. Okay. Even for the force between moon and the earth, for example, if the mass of the earth is, if for some reason starts to change, then the force on the particle of the moon, which will be just gm by r square, gm by r square. You know that the gravitational force F, for example, is minus gmm by r cube into r, right? Position vector r. And suppose this is Earth, and that's your moon. And let us put the origin at the center of the Earth. Let us say. So any point here, that's your, let us say y, for example. So here it becomes y. So for a small particle of the moon, it is minus gm then dm. Okay, dm for a small particle into y, the position of that particle from the center of Earth, divided by y cube. And if mass of the Earth is changing, for some reason, then this m is a function of time. And that's how you get time dependence. Okay, from here, let me actually write down more nicely. So we just saw that df, for example, the small force. So you have this Earth and moon, and supposing here is the origin, and any point is y, and think of a small particle here, then df can be written as minus gm dm over magnitude of y cube into y, and then dm can also be written as minus gm rho y over y cube dv, and therefore df by dv, so body force that is induced by this gravitational load b by t is simply df by dv, which is, and of course here it is vy minus gm rho by mod of y cube, and you have a y also in the numerator, gm rho y. Okay, so that's the body force induced by the gravitational load. Okay, so this is one kind of body force. You can have, of course, many other kinds, and all of them you can simply write it as b as a function of y and time t. All right, so having identified all forces on this body dt as b of t, b of as body force and traction force, we can come back to that linear momentum balance principle, right? Which is that net external force is equal to d by dt of total linear momentum of the part of the body. And now force has got two terms. One is the volume integral over d, right? And that's d y, isn't it? Plus the force due to traction. That's the surface of the surface, and the surface will be known by del d. Okay, that's useful in mathematics. D body, del D denotes the surface of the body. And this will be integration of traction force. Traction is a function of y, t, and the normal n. And then here you have d, a, y. Okay, and so this is the total force, and this should be equal to d by dt of linear momentum. So what will be the linear momentum of this dt? How can you get that? Notice that this dt is such that you have different velocity at different points. The velocity is not the same. It's a deformable body, and they are not connected to each other in a simple way. So you can think of, for example, just a small particle or small mass whose velocity would be dm times the velocity v, right? And dm you can also write it as rho v dvy, isn't it? And each of these are Eulerian functions, rho bar, v bar. So this is the this is called dp, infinitesimal linear momentum. And this you have to integrate over the entire body to get your p. So this is then integration over the entire body, that is dt, rho bar v bar dvy, right? We can see that. So you see, this is the integral form of linear momentum balance. And it is also kind of global in nature because it is not for a small, not for a location y, it is for the entire part. Okay, so we say that this is integral form of linear momentum balance, LMB, and also it is global in nature. By global we mean it is not for a local point, it is for the entire part of the body. That is why it is kind of global in nature. Okay, we want to derive differential equation from here, which will also be local in nature, which would hold at every point of the body. So that is our goal. Just like for mass, we had del rho by del t plus divergence of rho v equal to 0. So that differential equation holds at every point of dt. Likewise, we want to derive here local form of LMB. To be derived. Okay, so this is something we'll do in the next class, okay?
So you said that this form of linear momentum balance is not valid for the system whose mass is changing.
Sorry,
This form of linear momentum balance is not valid for the system in which the particles are changing. I mean, one particle is
yes,
coming.
correct. Correct.
But sir, if we will see, if we will see this capital P as mass times velocity, mass means mass of the whole body, times velocity of the whole body. Like suppose if the velocity of each and every particle is same, so then if we apply the chain rule, so it will be dm by dt into v plus m into dv by dt. So
Right.
it is valid for, so the term dm by dt is also coming soon. particles can exchange.
Okay, so I think this will become more clear in the next class. What I meant when I said it is only for a fixed set of particles. It should be, the system should be closed with respect to mass transport. So I'll clarify this more in the next class, okay?
Okay.
Let me first derive the local form and then it will become more clear.
Okay, sir.
Yeah.
Yes. Sir, so my first doubt is like when we are deriving this, we are considering this body as rigid. So like
No,
in that,
we are not considering the body.
okay, so but we
Why do you think
started
we are
with
considering
LM.
body as rigid? It is not rigid.
So like at the start, we
Well,
told now that we need to write LMB for like solid body. So sorry,
no,
sir,
it is
not
not.
rigid, solid.
No, it is also not so. I didn't say it is for solid body. It is for, see, whatever we are doing in this course, it is for everything. Why do you think that I never said it is for just for solid body? It holds whatever I have said till now. It holds for both solid and fluid.
Okay, sir. And sir,
Just have no confusion about it.
one more doubt I had was
Yeah.
like it is a follow-up question from Subham's question only. Like in fluid mechanics, we had to define the control volume to do the analysis.
Yes. Exactly.
Uh,
So let's wait for that thing. Okay. We will come to that in the next class. So these are of course related. The control volume, control mass, and can we have a system in which mass is changing and we still apply LMB? So all these questions are related. Okay.
yes.
So let us wait for the next class.
So we have considered the part of the body, and
Yes.
we said the particles of the part are actually not moving out, or not all other particles from outer portion of the body are also not coming
Right.
in that part.
Correct.
So
Correct.
we derived all of these things for that, but we can really say that the particles are actually not moving out or not coming in. The body is continuously
Yes, we
deforming,
can
so
say
the
that because
particles are
we,
moving all around the body, inside the body.
yes, particles are moving all around, but you see in this equation, for example, that you have right here, this integral equation, the domain is dt. As the particles are moving, this domain dt is also changing. So you are always looking at the same set of particles because this domain is changing. Okay?
So, sir, it is like all those particles that we selected earlier in the D, the
Yes.
part of the body. So when the body is changing with time, when deforming it is, so the particles are moving all around. So we are picking only those particles that we have considered earlier.
Exactly.
Define
We
D.
have taken only those particles that we considered in the first place. So we are always looking at only those set of particles.
So the particles will be all
And
around.
it is just
All,
fixed. It is just, you have to fix it in the beginning, but it is arbitrary. You can choose any set of particles and then you just have to track it, how it is moving. But you can choose any set of particles. But once you have chosen it, you have to stick to those particles.
so it is like that. The D portion is not physically, means it is moving inside the body actually, but it is not that it is whole physically moving. It is like we are imagining all of those particles in this D portion only.
But dt is changing, no?
Yes, D is changing, but the particles which we considered in D earlier is all around the body when the body is
Yes.
deforming. So we
Yes,
are
those
kind of
particles are not changing.
so those particles are not changing, but for the calculation point of view, so we are imagining all of those particles in this D only, and so we are
Right.
making it key. It is moving physically in body all around.
Exactly. So the particles are not changing, but the region occupied by the particles, that is dt, that region is changing. And all the things here, as you see, they are integration over the region. They are not integration over the particles, right?
Yes, sir.
They are integration over the region. Therefore, the domain is changing with time. But the particles are the same.
Okay, sir. Thank you, sir.